Okay, so maybe I can start introducing José Carlos del Toro Iniesta. It's a great pleasure to have José Carlos here today for this seminar. He studied in Granada and in La Laguna, where he got his PhD. Is it correct, José Carlos?
It is.
But well, he spent part of his career in Instituto de Astrofísica de Canarias and then also in Lockheed Palo Alto research laboratories. And since 1998, he's staff member at the Instituto de Astrofísica de Andalucía, and he was the director of the institute from 2004 to 2007. José Carlos is an expert of spectropolarimetry and is involved in many cutting-edge present and future solar missions. Just to say, among the others, is the co-principal investigator of the SOFI magnetograph for the European Space Agency Solar Orbiter mission, and is also the principal investigator of TUMAG for a magnetograph for Sunrise 3. José Carlos' collaboration with the Tor Vergata Solar Physics Group dates back many years, but it's always a pleasure to work with José Carlos on different topics, as the scientific and cultural interest and the fun about it is always the priority, let's say.
Absolutely.
So it's really a pleasure for us to hear from you your personal view on spectropolarimetry.
Thank you very much, Luca, for the introduction, and thank you very much for the invitation. I'm honored to be with you today. I'm fortunate to have been invited to speak to you about what I do every day, what I like most, which is spectropolarimetry, and well, certainly I will give you my personal view, because I couldn't do otherwise. So I couldn't give you someone else's view. So in some regard, the title of my talk, if you allow me, I'm going to share my screen. So in some regard, the title of my talk is tautology. Okay, so it is normal that I'm giving my personal view, and on behalf of my own group, the Solar Physics group at the Instituto de Astrofísica Andalucía, of the CSIC. CSIC is the biggest research organization in Spain, and the IAA is one of the 120 institutes belonging to CSIC. And I also speak on behalf of the Spanish Space Solar Physics Consortium, which I lead right now, which I coordinate right now, which is a set of 5 institutes working together back from 2002. So as Luca commented on, I have many friends for long in Rome, and this is always a special motivation to talk to my friends, and since I know we have cultural mutual interest, let me start by epistemology instead of pure science. I think it's important to realize what we do every day, and astronomers are nothing but photon counters. So we count photons. We cannot measure the sun or stellar or other heavenly physical quantities. Okay, so please mistrust anyone saying the measured temperature of this object is or the measurements of the galactic magnetic field are, etc. We only measure light, okay? So perhaps some smart colleagues of us measure neutrinos and gravitational waves very recently, but we are more humble and infer physical quantities of the sun from the measured light and some physical assumptions. These some, in many cases, are many physical assumptions, and then we must realize that assumptions are within our so-called measurements. Okay, so if we are photon counters, we better sharpen our skills for counting photons. Okay, counting photons in the best way we can. So, what does spectropolarimetry mean? Well, we count photons. So we measure photons, hence metry, the polarization state, hence polari, of the spectrum, hence spectral. So spectropolarimetry is the most comprehensive way of measuring the properties of electromagnetic radiation. So it is clear that the finer the analysis we do, so either in the spatial or spectral resolution, or the finer sensitivity in polarization, the better. But most importantly, the less noisy our measurements are, the better. So since we count photons, we need those photons, the level of those photons above the noise level. So noise is the real killer in any of our measurements. Spectropolarimetry is indeed a 5-dimensional problem. Here you see 3 dimensions of this problem. We have 2 space dimensions, the surface of the sun. Here we have a couple of sunspots, and the 3rd dimension, which is wavelength. Just by a simple glance, I should say these are data taken by Bruce lights from Hinode. So and these 2 are the famous pair of iron 1 lines at 630 nanometers. Just by a glance to these lines, we see convection in action, because we are looking at the wiggle of the lines. So bright granules, those granules in here have a bright continuum, and lines shifted to the blue. So matter is approaching us, and dark intergranule lanes have matter going inside the sun, so shifted to the red. So just a simple glance to this spectrum is a glance to the Doppler effect. But we also see the Zeeman effect. You can see how a single line converts in 3, splits in 3. Here is also split in 3, but they are less split, and they are not that clear. So so split in 3 in this line. So this is a consequence of the magnetic fields present in the sunspot. So we have to extract the information of these light in these 3 dimensions, but also in the 4th dimension. Then I have prepared a movie in which you are witnessing the 4th dimension. Imagine we cut this block in a given slit across this surface as this one. Okay, so we are cutting the block and see the spectrum of this line. You see the dark spectrum of the sunspot, but this is Stokes' eye. Here you see linear polarization, Stokes' view. Stokes' view, so linear polarization at 45 degrees, and Stokes V is circular polarization. You are seeing that the information is different in each of the 4 Stokes parameters. Now we cut the block at a given wavelength and image the sun in Stokes I, as in here, in Stokes Q, linear polarization, in Stokes U at 45 degree, and finally in Stokes V. From the different aspects that these images are offering us, we are able to interpret this message in terms of the physical quantities of the sun. Okay, well, I said it is a 5-dimensional problem, but the 5th dimension is time, because many times, in many cases, we are obliged to observe time series in order to study the evolution of structures or to study the interior of the sun by helioseismology. So our job is similar to that of a detective, because we have to measure the fingerprints that physical mechanisms leave onto the light we measure. So our measurements are the Stokes profiles as a function of lambda, of wavelength. So we measure I, Q, U, and V. So T means transpose, because it is customary to have this as a vector column. This means nothing. To find the suspects. Suspects are the physical quantities as a functions of the optical depth. We know that the atmosphere of the sun have temperatures, pressures, 3 components of the magnetic field, and velocities that vary across the atmosphere. So, as I said, physical mechanisms like absorption, emission, scattering, convection, Zeeman effect, Doppler effect, Hanle effect, and many others leave their fingerprints that we must interpret. Okay, and our only way for interpreting those fingerprints is the Reed transfer equation for polarized light. Okay, here you have it is a simple linear differential equation, but it is also a 4 differential set of coupled equations. Okay, because you cannot solve independently for I, for Q, for U, or for V, except in very special occasions. Here you have K, which is the so-called propagation matrix, and this is the source function vector. Source function vector somehow tell us the sources of light, which are in the matter, and the matter light is going through, and the rest of properties of that matter are included in a nonlinear way in the propagation matrix. Okay, so again, our measurements, Stokes vector, goals, the physical quantities, the ruler, the equation plus assumptions, because we cannot solve this equation without assumptions. Then we have to realize every single day that what we call measurements of T, P, B, gamma, phi, V are subject to assumptions, are simple inferences that depend on the assumptions. Fortunately, we have a robust system, because we can solve, well, we know how to solve this equation, okay? But this is not our problem. If you realize, this is an equation where the unknown is I, Stokes I. But in reality, this is the known quantities, because these are the measurements. So we have to invert this equation in order to find out these quantities which are non-linearly within K and within S. Okay, So, and as I say, we fortunately have a robust system of inversion in which we can go step by step, and it makes sense to increase or decrease the level of assumptions in order to get more detailed solutions to our problem. So I said we know how to synthesize, how to simulate the Stokes spectrum, but the whole problem, then, when it is far from local thermodynamic equilibrium, is that very difficult. Oh, excuse me. Oh, come on. It's a very difficult and iterative problem. If you have a model atmosphere, you can calculate the collisions that occur with matter in that atmosphere, and you prescribe a magnetic field with collisions and magnetic field. You can write down the radiative transfer equation and the statistical equilibrium equations. Once you solve these equations, then you calculate the density matrix elements that are also needed in the radiative transfer equation in order to find out a synthetic Stokes spectrum. Okay, if this synthetic Stokes spectrum is convergent because it produces collisions and radiative interactions that are compatible with the former ones, then you have solved the problem and you have synthetic Stokes parameters. If not, you have to iterate again. So the so-called local thermodynamical equilibrium approach is simpler because the iterative problem is broken, and by simply prescribing a model atmosphere, you can calculate the propagation matrix and source function, then solve the radiative transfer equation and synthesize the Stokes parameters. But as I told you, our problem is different. We don't want to synthesize parameters. We do want to interpret measured Stokes parameters in terms of physical quantities. Then we need to include a further iteration in both situations. Here, after synthesizing the Stokes spectrum, suppose that you have already a converged a synthetic Stokes spectrum, you have to compare it with observations. If these are good enough, then you have your final model atmosphere, okay? But if not, you have to modify the model atmosphere. Oh, I'm very sorry, but the touchpad is too sensitive, okay? You have to modify the model parameters and then start again. And in LTE, you have an iterative problem as well because of the same problem, because you have to compare two observations. And this is important because theory for nothing is useless. So, and our theory is very, very useful because we can compare it with observations and see whether or not our solution provides a good approximation to the final model atmosphere. Robustness. I said our system is robust, and I think this is a good demonstration of this robustness. On the left, you have a model atmosphere parameters. In the central column, you have I, Q, U, and V spectra of these two lines we saw formerly at 630 nanometers. And to the right, there are the differences between synthetic, synthetic spectra and observed spectra. As a matter of fact, everything is synthetic because we are simulating the sun. The sun is simulated with these black lines. So here you have the stratification. So the upper part of the atmosphere is in here is locked out, and the lower part of the atmosphere is this one. Okay, so the synthetic sun is in black lines. You have that the quantities vary with depth. Okay, and the first assumption is that they are constant, and we invert. The result is in green. Well, of course, it differs. There are mistakes, there are errors. Okay, some percentage errors from the original profiles. But I would like to focus your attention to this. Look at the result. So this is, if I assume that the quantities are constant, the result is some kind of average of the real values in the trustable part of the atmosphere I can probe. So the shades are errors, are indicating where you cannot trust the results because you don't have enough information. Okay, so you can only trust the results from, so to say, minus 0.5 to minus 3 in log-tau. Okay, so in this trustable zone of the atmosphere, we have averages. We have averages of the real quantities, and they are pretty nice averages. Okay, so let's go to a further step and assume that the quantities are linear. Well, look at this. So these linear approach are pretty close to what one expects to measure just by eye. Okay, and clearly the red approach, the red profile, approaches better the black profile. So the errors are much smaller. If we go further away and assume quadratic variations with that, we have the blue profiles. Then the result is even better, and the profiles are even closer. The errors are even smaller. So we can think of the measurement problem as an expansion series where successive approximations are given a better description of the function. Okay, and this is very good. Excuse me. So we need to measure, and the measures should image the sun, should map the sun, and for this we have telescopes and image stabilization systems as those in the SOFI instrument, which is now flying in the solar orbiter mission. This is during the integration phase at MPS Göttingen. Okay, so we need to carry out polarimetry, and we do that by LCDR-based polarimeters like the ones you see in here. They are also flying right now. And we do spectroscopy as well. And we carry out spectroscopy both with Fabry-Perot etalons like this one for SOFI, or with spectrographs, with classical spectrographs. So we do everything an astronomer can do with light. So image, polarimetry, spectroscopy, diffraction limited imaging, differential imaging, because polarimetry is indeed differential photometry. Okay, but in sometimes, like in SOFI, we are that far from the sun. By the way, in a few days, solar orbiter will be in perfect conjunction with the Earth, so it will be right behind the sun. For the first time, humankind will be able to image the whole magnetic field of the sun from the Earth, and the backhand from the hidden part of the sun. So we'll be that far, and it will be that difficult to communicate with Earth, that we need to do science aboard this, the instrument. And this is carried out by means of an electronic inverter of the radiative transfer equation, the specially devised FPGA, which is developed here in Granada, and which is more than 50 times faster than regular computers on ground. Okay, and this is only in charge of carrying out those electronic inversions of the transfer equation. Just for you to understand the measurement principle of our instruments, of our imaging spectropolarimeters, you can take one spectral line from the source spectrum and sample in several wavelengths. Here, 5 through the line plus 1 in the nearby continuum. So if we carried out images in each of the 6 wavelengths, we have the classical 3D spectroscopy, as our night astronomers are so proud to say. But we are not happy with 3D. We need 4D because we need to carry out 4 different measurements in each wavelength, because we are interested in the 4 storage parameters, I, Q, U, and V. This is the same sunspot as seen in I, Q, U, and V. And this is made by taking 4 different measurements at each wavelength. Here, the spectral line, the observed spectral line is in blue, and in red, you have the filter profile, which is scanning the line sequentially. So every set of 24 images, 6 wavelengths, 4 polarization states, produce one of these set of 4 maps. But we cannot send these 24 images to ground because we are that far, and then convert with that electronic inverter, the transfer equation, these 24 images in just these 4 ones, B, gamma, and V, the 3 components of the magnetic field, plus the line of sight velocity. When our means for spectral analysis, instead of an Etalon, of a Fabry-Perot Etalon imaging instrument, is spectrograph based, then what we have is to scan the solar scene with a slate, producing each time, for each location of the slate, spectrograms like those in here, I, Q, U, and V. So the wealth of information which is in these kind of spectrograms allows us to map for instance, the magnetic field strength in here. This is courtesy by NAOJ and our data from the satellite. Okay, so but I said, excuse me, that I was giving my own vision, my own experience, and this is that of my consortium, the Spanish-based Solar Physics Consortium, which so far has participated in these missions, Sunrise 1 and 2. Sunrise is a stratospheric balloon mission which flew twice in 2009 and 2013, led by MPS in Göttingen, Germany, for which we provided IMAX, the Imaging Magnetograph Experiment, which is fully Spanish. I should say that this is the first aerospace magnetograph made out of the United States, and it is also the first aerospace instrument fully conceived, designed, built, and flown by Spanish institutions. IMAX was somehow a technology demonstrator that liquid pistol and variable retarders and Fabry-Perot Etalons could flew in space, and this was the reason for ESA to allow our proposal for PHI, the polarimetric Angelos Aismic imager, to be a reality. I co-lead with Professor Sami Solanki from Max Planck in Göttingen the instrument, and we are indeed preparing PMI, the photospheric magnetic field imager, for the Lagrange mission, which is not in the science program of ESA, but in the space safety program. Okay, so but we are now developing a similar magnetograph to FI, but just with one telescope for the Lagrange mission. We are also engaged in the Sunrise 3 mission, which is of course led by MPS, prepared to be flown in 2022. And this time we not only contribute with a magnetograph, which in this case is a brand new magnetograph, which is tunable in spectral lines, but it uses visible wavelengths. But we also collaborate with our Japanese colleagues in the Sunrise Chromospheric Infrared Polarimeter, which is a spectrograph-based instrument. Okay, so but as a consequence of our expertise in space, we also have participation in ground-based projects like DECIST. We are preparing, in fact, it is the Inversion factory, which is an extension of our electronic inverter for the radiative transfer equation. And we have also prepared a different kind of that electronic inverter for EST. Plus, we are now, together with Sweden, Italy, and Germany, preparing the tunable band imagers for the European Solar Telescope. S3BC is not only formed by my institute, IAA, but also INTA in Madrid, the Instituto Ignacio de Riva of the Polytechnical University of Madrid, the University of Valencia, and the IIC. Okay, so our experience was IMAX, which flew in Sunrise 1 and 2. This is schematics of the optical unit. Light enters through here, goes twice to the etalon in order to thin the filter transmission path. Well, first is modulated in polarization. Okay, so light goes through here to a beam splitter, which divides the two orthogonal states of light to the two cameras. This block is the proximity electronics, which, among other things, provides high voltage power supply to tune the etalon, which is inside this oven. This is the real stuff. This is the real hardware of the optical unit of IMAX. Here you recognize the proximity electronics and the etalon. So these are the pre-filter plus the liquid crystal variable retarders. And here you have the electronics unit of the instrument. This is SOFI. This is SOFI just some days before launch, before sending it to Stevenage for being integrated into solar orbiter. As you can see, it has two apertures of the two telescopes. It has one high resolution telescope and a full disk telescope. This is the main mirror of the high resolution telescope, and this black tubing here is that of the full disk telescope. That tubing here is the common path for both telescopes, because here we have a fit select mechanism by which we select between the high resolution and the full disk telescope. And this is the simpler in appearance electronics unit of SOFI, where the electronic boards are stacked on top of each other. Here you have the only redundant system of our instrument, which is the power converter module in these two stacks. Here is the analog heater mechanisms driver electronics. This part is shared by the tip-tilt controller, which is in Sophie, and half board of the DPU, and in a whole board for the DPU. The DPU is formed by 1.5 electronic boards. And finally, and separated and isolated from the others, is the high voltage power supply to tune the etalon. In the case of SCIP for sunrise, our objective is to see the chromosphere. It's a sunrise chromospheric infrared polarimeter. These two regions of the spectrum will be imaged in the spectrograms, and those regions are plenty of lines whose formation heights are in the chromosphere. Okay, so we'll have information from the chromosphere with this instrument, whose optical unit looks like in here. Light enters, and first is polarization modulated, then part of the light goes to a slit jaw lens and recorded in the slit jaw camera. Then here you have the slit, the collimator mirror, the camera mirror, the collimator, the grating, the camera mirror, and then light is divided with a dichroic to the camera recording the 850 nanometers and the camera recording the 770 nanometers. In the case of 2MEC, you know, the imaging Fabry-Perot is different, and then we are sampling wavelengths across, imaging the sun at those thin wavelengths marked by the discontinuous red line, which is the result of multiplying this the spectrum of in green you have the source spectrum, the FTS spectrum of the 50 to 50 line and the magnesium line. Okay, in blue you have the real pre-filter profiles that is in charge of suppressing the side lobes of the Fabry-Perot transmission, which is, as you know, periodic. And then the final profile is in this one, and this is similar in the case of the magnesium line. As you can see, the pre-filters, the real pre-filters do a good job in suppressing the side lobes. And this is how the new, I'm sorry, I have to wait until this animation, oops. So this is how 2MEC looks like. Well, indeed, you can discern some boxes. These boxes are important for isolating thermally each subsystem. Okay, but here light enters through here, and you see the first difference, which is a filter wheel, a double filter wheel, where we have the pre-filters for selecting the spectral lines we have to measure, plus some optics for calibration, some optics even for polarimetric calibration. Then light goes to this flat mirror, goes twice to the Fabry-Perot, because here we have two folding mirrors, okay, and then goes to that another mirror, which and then drives light to the beam splitter, which puts light in the two orthogonal polarization states in the two cameras. We have a dual beam polarimetry. And just for you to understand which is the light path, you can see this animation. So it goes to the filter wheel, the polarization modulator, the flat mirror, twice through the etalon, the flat mirror, and then divided in 50% to each of the cameras. These 50% of light are the two orthogonal polarizations, a product of the polarization analysis. With these kind of instruments, we've been pretty successful, I would say. This is a movie I love because it illustrates the capabilities of our imaging instrument. This is a movie made during the first flight of IMAX, and it lasts for half an hour. Here you have the intensity, the continuum intensity. You are recognizing the swimming pool effect coming from the solar oscillations. So this is velocity in kilometers per second. Here you have a magnetogram. So this is a wavelength of the circular polarization. So it is indicating that there is polarization, hence magnetic fields, very small scale magnetic fields. The scale is in arc seconds, by the way. Okay, so these are 10 arc seconds. So you can realize the very good spatial resolution. But the important thing, we discovered these otherwise ugly images with black spots. Every small black spot is an indication of linear polarization. Our sensitivity has never been surpassed so far, and indicated that the sun is overpopulated by inclined, very fairly horizontal magnetic fields everywhere. So with these kind of data, we resolved several puzzles, and for instance, we see for the first time isolated flux tubes, and solved real puzzles in solar physics as the interaction between magnetic fields and convection in the photosphere. Okay, so we solved these problems because we were observing directly all the steps that the formation and evolution of small-scale magnetic fields take place. Here in blue, you have in blue and red is a tachogram, velocities. So this is a granule which is ascending and dragging up a magnetic loop, which is indicated with these two polarities in blue and red, and this green linear polarization signal. So here we have a loop ascending. So the flux, magnetic flux, is exposed to the surface by the action of convection and granulation. Once it is exposed, it is concentrated. It is advected by convection in particular places. It concentrates in particular places where you can see how matter and magnetic fields are moving, and they are producing stronger and stronger magnetic fields that in the end collapse when surpassing the given level and form a single magnetic flux tube. This is a magnetogram, and the colors indicate intensities. This is a contour map. Okay, but this flux tube is not rigid. It has a life. Okay, because it oscillates and it fragments and later coalesce in a dance which is very beautiful, and that we could witness with our eyes by analyzing the data. Here we have also data, but these are not processed data. These are not real data. However, these are coming from solar orbiter. These are coming from the full disk telescope. Here you have the photospheric continuum. The sun was very clean, very quiet at that time, but in the magnetogram, so green and brown indicate different polarities. In the magnetogram, you are seeing that we had a active region waiting for emerging to the surface. And this is the classical view of a tachogram where half of the sun is approaching us, half of the sun is going down. So the sun is rotating. And these are the same, but for the high resolution telescope. We were at 0.5 astronomical units, and with a 12 centimeters telescope, you can see the spatial resolution we had, and we were only at 0.5. So orbiter will reach 0.3. And I would like to stress that these two images have been produced by the first time that humankind has produced magnetograms and tachograms without human intervention aboard a deep space mission. So these were produced aboard SOFI and were downloaded from it to ground. This is my last transparency, and I always like to go back to my first one. So I would like for you to remember that indeed everything I've shown you, although it is labeled with magnetic field strength or line of sight velocities, etc., they are not measured. They are inferred physical quantities, because we, at least our team, I don't know others, we only measure electromagnetic radiation. We are photon counters and interpreters. The future will tell whether we are smart or not. We infer physical quantities from the measured light and some robust physical assumptions. Okay, physics is needed to understand the message sent by solar light, but it seems that we don't do it that bad, according to the images I've just shown you. Thank you very much.